In this segment, we're going to look at Hooke's law graph in an inverse way. So typically, as we've seen previously, Hooke's law's force applied is K delta x, and it's in the form of y equals mx plus b. And what that means is that the elongation is the independent variable. So when one is conducting an experiment, you might stretch the spring a certain distance and then see what the force is, which makes the force applied the dependent variable. Well, one could just as easily, conduct an experiment where you stretch the spring to a certain force and then measured what the distance was. In that case, the force would be the independent and the elongation would be the dependent. So it depends actually on how you set up the experiment. So the inverse relationship, we have the y, which is the dependent, and the x independent. Our axes are switched. We saw previously where we have elongation and force. So that means here we have force and elongation. So what does that mean in terms of the equation? In terms of the equation, starting with the force applied equals the spring constant times the elongation, and we have our y equals mx plus b. We see that the slope is the spring constant. Well, if we switch this around, so we have a delta x equals, so this switches from becoming the independent to the dependent, we would switch the sides. So, switching the sides, we've now just crisscrossed the formulas. So we have k delta x equals force applied. And now we're going to solve for delta x by dividing both sides by k. Since k divided by k is 1, we're left with delta x equals force applied over k, which we can rewrite as the force applied times 1 over k. And this has the interesting element that the y-axis is now delta x. It is now the dependent variable. And the force applied is the independent variable. And typically in these situations, the y-intercept is equal to 0. But that means that the slope is now 1 over k. In a typical arrangement, the slope is the spring constant. When we switch the axes, the slope is 1 over the spring constant. So what that looks like when we see the graph, here we have force applied as our independent, and we have 3 examples of dependent where we're measuring the elongation. We have our data for 3 different springs. We stretched each of them with a fixed force and then measured what the elongation was, and it yielded these 3 curves. And I noticed the axes are switched. We have force applied and we have the displacement like so. And you'll notice the equations 0.33x, 0.16x, and 0.11x. And our equation we have is the y-axis is delta x, the x-axis is force applied, and the slope is 1 over k. Y-intercept is equal to 0 since it goes through the origin, like so. So if the slope is 1 over k, 0.33 equals 1 over k, then k equals 1 over 0.33, which is 3. And if we take the second example, we have 0.17 equals 1 over k. Then k equals 1 over 0.17, which is 6. And if we take the third example, which is 0.11 equals 1 over k, then k equals 1 over 0.11, and that equals 9. Now, we'd seen in an earlier example where we had spring constants of 3, 6, and 9. Now, when we're graphing, switching the axes, The weakest spring is now this one. Because 1 over 1/3 is 3. And the shallowest one is the strongest, because we see that it's 0.111, and that is 9. And the one in the middle is 6. So we have to be careful when we are looking at different examples and graphs of Hooke's law. Are the axes F versus X, which we would expect most of the time, less commonly, but we still do see it, delta X on the vertical and F. And in this case, K is the slope. And in this case, the slope is 1 over K. And that is the case of inverse Hooke's law graph.